the meaning of a carrier wave and the meaning of the word intelligence. So let's start with the intelligence. Intelligence is something worthwhile you want to transmit. For a ham radio operator, intelligence could be very well your voice. You want to talk to a microphone and have a conversation with a fellow ham radio operator, perhaps at a great distance in a foreign country or on a different continent. So human voice is a predominant version of intelligence, but that's not the only kind of intelligence we will work with. Ham radio operators often use intelligence in a digital format. You actually work at a computer and you punch in something at a keyboard, or you transmit a file that is already on your hard disk, and that file in digital format would go into your ham radio transmitter and would do interesting things there. That file could well represent picture elements of an image, or it could be an outright typed text. So for intelligence, now we have a digital format of the intelligence, we have voice, we have Morse code, and we have to mention that intelligence is really widely used in the industry as well. In an industrial environment, intelligence may be any of the physical parameters in that plant, such as temperature or pressure, or the flow of fluid, or a parameter of a solution called pH, and so on. So all of those physical parameters must be then converted to an electrical format. The same way, human voice must also be converted to an electrical format. This is achieved by talking to a microphone. And the microphone, what the microphone would do, it would convert the pressure wave from your mouth. This pressure wave will be converted to a proportional electrical wave. So any kind of intelligence we like to transmit with a radio, ham radio, or a government radio, or an industrial radio, because they are all similar, any kind of intelligence must first be converted to an electrical format. That goes for the physical parameter, that goes for a picture, for a voice, and so on. Now, voice is really an important aspect of intelligence. Voice is what we want to transmit the most times. But how far can voice be carried? If I speak up here, I am heard by you in this room. If I start talking really loudly, maybe I'm heard downstairs. If I'm really yelling hard, then maybe my voice would carry over a field. But my voice would not carry over the other side of this country. My voice just will never arrive to a foreign country, or it would not be able to cross an ocean. So now we need something, another phenomenon that has the property to propagate, to travel great huge distances. And we will combine the two. So we will introduce the carrier wave. The carrier wave is a wave that can travel any distance around this planet. It can carry intelligence. If we impose the intelligence on the top of the carrier wave, it can carry the intelligence one way or another. Let's name two countries, our great country Canada, and pick out the country of New Zealand. If you look at the globe, you will see that there is a shortest distance between Canada and New Zealand, and then you go around the other way, there is the longest distance from Canada to New Zealand. So a carrier wave is able to propagate either the one way or the other, so from any point of Earth to another point on Earth. One natural carrier wave would be a radio wave, or an electromagnetic oscillation. Now, scientists studied this and concluded that gamma rays, X-rays, microwave radiation, visible light, invisible light, and radio waves. They all fall into the same category. They are electromagnetic waves. So now we have our carrier wave. Our carrier wave is an electromagnetic wave. An electromagnetic wave can travel huge distances, even in outer space, such as from our moon to Earth, or from sun to Earth, or from a distant galaxy. And those waves are not necessarily visible light waves. They could be radio waves, and they are studied in the domain of radio astronomy. So now we know that we want to harness a carrier wave, and we impose our intelligence on the top of it, and this whole process is called modulation. So modulation is the process of impressing some physical parameter of a carrier wave in step with the intelligence. Well, the carrier wave itself would leave your ham radio station from the antenna. So your radio would create a radio frequency oscillation, and your microphone would create the electrical format of the audio intelligence. And the radio electronics in the enclosure, really complicated circuits, would allow the electrical image of the voice to be impressed over the top of this radio frequency alternating current oscillation. And once this is done, the resultant, the modulated wave, is sent to your antenna, and the antenna would act as a transducer that would convert the radio frequency oscillation into the electromagnetic wave. What if we would try to just radiate our carrier wave without any intelligence? Would that be possible? Yes, it is. Indeed, it's very possible, and ham radio operators even use this mode. We use this mode when we want to tune up our radio transmitter, because the radio transmitter must be merged into the antenna. Again, the meaning of this merge is that the power you send from your radio station up into the antenna does not travel back and forth and back and forth. The antenna must be capable to absorb this power. When the antenna is absorbing all of the power from the transmitter, we have a merged situation. When we have a merged antenna to a radio transmitter, then we can start modulate, because the antenna and the transmitter, they are already merged up. Now we can talk to the microphone, modulate that carrier wave, and send our intelligence over it. So I am not trying to force mathematics on you, but I'm certain that you know this, that a sinusoid or a cos wave in a mathematics class is written up like this. Now we want to interpret this. Lowercase e brackets t would mean the instantaneous value of this parameter as function of time, and e of t could be the instantaneous value of a voltage somewhere in your radio transmitter. Capital A is the amplitude. The amplitude is the greatest swing the sinusoid can swing away from the resting value or from the zero crossing in the positive or in the negative direction. So the maximum value is also called the amplitude. And a sinusoid has its amplitude modified by a sinusoidal change. The sinusoidal change, the sine function, has an argument in the bracket. That is the argument. It's called the angle. So a sinusoid is the amplitude times the sine function of an angle. A sinusoid is either a sine wave or a cos wave. Eventually there is no other difference in between the two but a phase shift. This phase shift is signified here by this phi. So a cos wave is a wave 90 degrees phase shifted opposite to sine. Now, why do we know or need to know this format? because we inspect this format and we immediately realize that if we impress intelligence onto this wave, we have to modify one of the available parameters. One available parameter would be capital A, the amplitude. If we modify the amplitude of a radio frequency oscillation, we perform amplitude modulation. What else can we modify? Look at the bracket. The bracket is called the angle. Whatever there is in between those two brackets, if we modify that, we would perform angle modulation. So far we have two versions of modulation: amplitude modulation and angle modulation. But the angle, the argument of the sine wave, has two different components. 2 pi ft is called the angular velocity. Think of the angular velocity. Maybe you sometimes visited the hydro generating stations where water is rushing down into a turbine, and a shaft is turning. It has coils on it to cut through the magnetic field created by some magnets. The angular velocity will be the rate at which that shaft is turning. Well, of course, hydro generating stations, they cannot turn very fast, so they would only generate a low frequency oscillation at 60 Hertz. And in radio communications, we would like to use frequencies many times higher, so high that we measure them in millions of hertz, called megahertz. So while we have a real high frequency, we still have an angular velocity to that wave. And if there is an initial phase, well, the initial phase would cause a shift. We will look at the next picture in an instant. Right now, I just finished this statement. Modify the amplitude of a sinusoid, you perform amplitude modulation. Modify the frequency in these brackets. By modifying the frequency, you perform frequency modulation. And by modifying the initial phase of a sinusoid, you perform phase modulation. So it looks like that frequency modulation and phase modulation are two aspects very similar to each other. Now just a quick by the way. What services are using amplitude modulation? If you travel somewhere on the highway and you turn on your car radio, you're approaching the Mackinac Bridge and you want to know the weather, you switch to, they have a frequency displayed on posters. And that's an amplitude modulated radio transmitter. So when you are approaching landmarks, bridges, or tunnels, and the managers of the tunnel or of the bridge, they want to communicate with you, they use amplitude modulated transmitters. Where else do we use amplitude modulation? Surprise, in avionics. If you have an amplitude modulation capable receiver, and you go out to the terminal to our airport in Sault Ste. Marie, you turn your radio to the right frequency, about 170 megahertz, and you can listen to cockpit to tower communications, because in aviation they use amplitude modulation. Again, there is an AM dial on your radio, and there are AM radio stations that they radiate music and news. Where is frequency modulation used? Well, frequency modulation is used by FM radio stations, whichever one is your favorite. 99.5, I'm listening to oldies, maybe 93.9. Those radio stations, they use frequency modulation. What about CTV? CTV is the last remaining analog television transmitter in our area. CTV is transmitting on channel 2, and television, analog television, such as the last remaining local station, they always use amplitude modulation for the picture. So television pictures coming your way, they are coming amplitude modulated. In the same time, there is a sound track next to the picture. And the soundtrack of analog television is frequency modulated. So television uses both amplitude modulation and frequency modulation. Those were just a few examples of those different type of modulation. Please scroll up to the curves. Those curves would be the representation of sinusoids. When you say sinusoid, you imply that a sine wave or a cos wave, they both are sinusoids. Suppose you look at those waves in a laboratory, that could be your high school or college or university laboratory or your own basement, because a fairly decent oscilloscope that turns your laptop or computer into an oscilloscope, you can have it for under $100. On an oscilloscope, one can display one or two waves. I'm displaying two sinusoids here on purpose, the red one and the blue one, and just to prove that a sine and a cos, they are no different from each other in any other aspect than just a phase shift. Now, whichever one is sine and whichever one is cos is really up to you to declare, because the whole image on the screen of your oscilloscope, you can shift it horizontally to the left and to the right, and whichever feature of those waves you bring them right to the left edge of the oscilloscope, that's your origin, that is your reference. So it looks like the red wave, the sine wave, starts with a negative going swing, and then the blue wave starts already at the high negative value, and it carries on from there on. So it looks like cos is leading sine, because cos already achieved its peak value and sine is merely zero crossing. This is how we determine which wave leads the other. So by looking at those waves, we see that along the horizontal axis we have the flow angle. So radio frequency oscillations, they have an angular velocity. The angular velocity measures in radians per second, and the radians per second would express how many radians per second did the wave rotate. So those are the features of a sine wave and a cos wave. And what's the conclusion I want you to remain with here? That sine and cos, they both are sinusoids. They are similar to each other, and they became sine and cos only when they are referenced to each other. And actually the referencing is your own choice, because you can declare one or the other as the reference. Next page, please. Here we are now, the two most important pieces of equipment any electronic enthusiast or ham radio operator can have in the basement. And surprise, this equipment does not cost thousands of dollars. Well, this is eventually a digital storage oscilloscope. If you need something that fancy, you can have it for about $500. So it really costs much less than a ham radio. However, a fairly decent oscilloscope you order in probably from China would cost you $80, and you connect it to your laptop, and you have a dual channel oscilloscope that would display such waves. So the oscilloscope operates in the time domain. Why? Is there any other domain than time domain? Everything is happening in time. Time is running here. Well, there's another domain called the frequency domain. Now, each time you sit in front of your television set and you're flipping the channels, eventually you explore the frequency domain. Because from Shaw Cable you have several hundred television channels coming your way, and those channels, they occupy a certain share of the available bandwidth. So those channels are next to each other. So each time you flip the channel, you start with a weather channel, channel 2, and you go up 3, 4, 5, 6, 7, 8, 9. You are just serving the frequency domain. So you are searching in the frequency domain. Now you select a particular channel you like, maybe channel 14, which is Detroit Public Television. You like to watch that channel, then that one channel would evolve in time. So an electronic signal that's present in your ham radio could also be inspected in the time domain and in the frequency domain. In the time domain, a signal is inspected, visualized with an oscilloscope. In the frequency domain, is visualized with a spectrum analyzer. Spectrum analyzers and oscilloscopes, they are coming from free to several $1,000s. There are free downloads for both oscilloscopes and spectrum analyzers, low frequency or audio frequency, of course, that they would turn the sound card of your computer or laptop into a audio frequency spectrum analyzers or an audio frequency oscilloscope. What is it you see on the display? The oscilloscope is capable to display a sine wave or a wave much more complicated. I purposely show here a sine wave again to remind you that a sine wave has an amplitude. That's the largest swing the wave deviates from zero in the positive direction, but the amplitude is the same as the largest distance the wave can deviate in the negative direction. So the amplitude is along the vertical axis. Along the horizontal axis, of course, we have the flow angle. But the angle is flowing in time, so the horizontal axis is same as time. Now, this is an interesting concept here. What you see, those vertical spikes, they are called components. And then there is a fundamental mathematical equation where we do not go into its use or development, but I will just say it with words for you because you absolutely must remember this. When two different sinusoids, they are multiplied together in an electronic circuit called the mixer or the modulator, which is part of your ham radio transmitter or receiver. Then you perform multiplication in the time domain. Multiplication in the time domain has another aspect. It leads to addition and subtraction in the frequency domain. The whole of ham radio and the ham radio electronics is based on this one principle. So what is it that you have to remember? Multiplication in the time domain leads to addition and subtraction in the frequency domain. So when you add and subtract in the frequency domain, what you will get are individual components. And those individual components are displayed here by this spectrum analyzer. Look at this as those components would be different channels of a CB radio, 24 channel or 40 channel CB radio, or different channels of channelized radio equipment, or different channels of your television set. So those are the two super important instruments that they display the waves in your ham radio. Next page, please. Oh, what's going on? Amplitude modulation. Amplitude modulation is a widely used type of modulation by ham radio operators. Any ham radio like this one, any ham radio whatsoever, always has a mode of amplitude modulation. But amplitude modulation sounds the nicest. If you have a ham radio contact and use amplitude modulation, you will get the best signal report because amplitude modulation has the richest, best sounding sound. However, amplitude modulation is not the most efficient one. So if your goal is really to score a real great distance to work an expedition on the South Pole or to make a contact to Africa or Australia, you will probably not use amplitude modulation. Amplitude modulation belongs to a Sunday afternoon network. So one alternative of amplitude modulation is telegraphy. Telegraphy indeed is an extremely important mode. It's debatable whether telegraphy is used more than single sideband voice modulation or it's used equally often. Well, we know that we have Bruce here, a CW enthusiast. Myself, I'm doing my best to make CW contacts. I am doing HF contests, and those contests, if you really apply yourself, you can work 200, 300, 400 contacts over a 2-day contest, all in CW. And well, I'm doing that, but we'll talk about that later. Right now, CW or telegraphy. If you have a telegraphy signal that would be fed to an oscilloscope, this is how it would look like. Those short pulses are the dots and the long ones are the dashes. Actually, there is software freely available. It's called CW-GET. The software installed in your computer. If you tune your ham radio to an ongoing CW contact, then on the monitor of your computer you start seeing the pulses. Not only you start seeing the pulses, this is the time domain display of that CW contact. In the same time, you also see the frequency domain, meaning there are CW stations next to each other. In more particular, during a contest, they are as close as 100 or 150 hertz to each other. If you are just working at your leisure, you try to work stations where the next one above and the next one below you are at least 1 kilohertz away. Nevertheless, this free software called CW-GET would give you the time domain and the frequency domain display of CW. Well, then there is AM proper. And AM proper has a carrier, a USB, and an LSB. Well, this is getting complicated. USB stands for the upper sideband, and the LSB stands for the lower sideband. And I wish that we would be allowed here to use some high school trigonometry, but we are not going that way. But I will remind you again that when you impress audio frequency intelligence onto a carrier wave, what you do there electronically, you multiply. And multiplication in an electronic circuit in the time domain would lead to addition and subtraction in the frequency domain. So you have your radio frequency carrier, say it's 29 megahertz for the 10-meter ham radio band. And your voice could have components, say at 2 kilohertz. Then 29 megahertz plus 2 kilohertz, the sum is called the upper sideband. And 29 megahertz minus the 2 kilohertz is called the lower sideband. So by modulating voice over a carrier, you create the sum, the upper sideband, and the difference, the lower sideband. And in between the two, there is the carrier. That was your 29 megahertz in the first place. DSB and SSB stands for dual sideband and upper sideband. Dual sideband and upper sideband, they are extremely widely used. Dual sideband is used as an intermediate step in lots of electronic communication equipment. Ham radio operators eventually do not radiate dual sideband signals. So the meaning of the dual sideband signal is that the carrier in between, after multiplication or modulation, you create the upper sideband, the lower sideband, and you have the untouched carrier in the middle. The carrier itself does not have an intelligence content. All of the intelligence, all of your voice is embedded into the upper sideband and the lower sideband. So this was learned early in radio communications, and modulators were developed which eliminate the carrier. We also call the carrier the dummy carrier because it does not have an intelligence content. So by eliminating the carrier, whatever available transmitter power you have in your radio transmitter could be invested in the sidebands only. We go one more step. The upper sideband and the lower sideband, they carry the exact identical amount of intelligence. What if we eliminate one or the other? by eliminating, say, the lower sideband and the carrier, then the upper sideband is the only component left. Now all of the available radio frequency power from your transmitter can be invested in the only one component worth having, because that's the only one component that carries intelligence. So advantage single sideband. Upper sideband and lower sideband, they both are called single sideband, and those modes are used on HF and VHF from the 20 meter band and up. We strictly use upper sideband, and lower bands on 40 meters and down to 160 meters, which is my favorite band. There we use lower sideband. So one more time, what's happening when we modulate? Talk to the microphone. Convert your voice pressure into an electrical wave. The electrical wave and the radio frequency oscillation generated in your radio go to the mixer or modulator. That is the stage that would multiply the two waves in the time domain to perform addition and subtraction in the frequency domain to create three components: carrier, upper sideband, and lower sideband. Well, there is one special type modulator that would create two components only, upper sideband and lower sideband, and would totally eliminate the carrier already. So that is called the balanced modulator. One up, please. Here we see the amplitude modulated wave as drawn up by a draftsperson. The lower frequency is the intelligence. This is how in a laboratory you would test your equipment. The intelligence could be a 1 kilohertz tone, and the carrier itself could be, say, a 7 megahertz radio frequency oscillation. When the two are multiplied together in the time domain, then the amplitude of the radio frequency carrier would start changing in step with the instantaneous value of the audio. If the audio amplitude is increased and increased, then the amplitude of the carrier can be changed so much until it's down to nothing. If this is happening, we say that we performed a depth of modulation of 100%. Is there a depth of modulation past that? Can one modulate more than 100%? Unfortunately, yes. If you increase the depths of modulation to 110 and 120%, then you start to reduce signal to zero either side of the zero crossing. So there will be narrower pockets and gaps of non-existent signal, and this would lead to distortions. So to have a distortion-free transmission, we do not ever want to exceed the depths of 100% modulation. This green on the background would be what you see on the screen of an oscilloscope. If you test a modulator with a test tone with a 1 kilohertz, and the radio frequency then is so high, it could be 7 or 14 megahertz, that the time period is extremely narrow. The time period is so narrow that the wave on the screen would describe one single oscillation on a very tight, narrow spot, which could be smaller than the electron beam of your oscilloscope. If you have an analog or a digital oscilloscope, either way, an analog oscilloscope has a beam, and a digital oscilloscope would have a picture element. So when the size of a picture element is larger than the flow angle of one single oscillation, then the radio frequency oscillations, they all touch together and turn the screen into a solid green. So the solid green is like that. There is radio frequency oscillation, but the oscilloscope can no longer resolve it. So there is no mistake here, nothing is erroneous. That's how an AM wave looks like on the oscilloscope. One more, please. This is what the spectrum analyzer would display. The spectrum analyzer works in the frequency domain. Right in the middle of the screen, there we have the carrier. Above it is the sum, 29 megahertz plus 2 kilohertz. Below it is 29 megahertz minus 2 kilohertz. This is just a numerical example, but that's what you would see on the display of a spectrum analyzer. One more, please. Dual sideband and single sideband signal spectrum. Again, a spectrum is displayed on a spectrum analyzer. So we have a modulator inside this ham radio. So I'm not showing the electronic schematic, I'm just showing what's happening. This modulator is fed with the radio frequency oscillation. That's a single frequency oscillation. So in the frequency domain, it shows up as a single vertical pulse. But the oscillations, imagine that you point into this. So the sinusoidal oscillation is running right perpendicular to this board. And it's running behind the board as well, but you don't see it because you look at it frontally. So what you see is that sine wave, as it oscillates, it's coming right into your eye, so you only see it going up and down, but it goes so fast up and down that you see a single stick, and that's the carrier. If the carrier and the intelligence signal, why are there so many components? Because as you talk, the human voice has frequency components from 300 hertz to several thousand hertz, but above 3400 hertz is not worth transmitting them because the intelligibility of the ear and the capability of the mouse in a human body, they don't overlap. A human mouse can talk up to 7-8 kilohertz, but the human ear does not hear it much. So it was found out that past 3400 hertz belongs to the opera house and musical instruments. So the telephone company, they draw this limitation. Anything below 300 hertz is highly worth transmitting. Anything above 3400 hertz, the ear cannot really hear it well. So when the signal is confined between those two limits, we call it telephone quality. But ham radio operators say that, well, what if we only transmit 2500 hertz? Or go down from 3400 another 1000 hertz? So a whole lot of voice content is left out. Are we losing now or gaining? Well, in a way we are gaining because, again, your ham radio only has, say, 100 watts power. And whatever available power now you have, you invest it into a narrower voice spectrum. So the outcome is that the narrower spectrum would be more loud on the receiver side, so you gave your signal more punch and a little bit less intelligibility. So that's why several components are shown here. And after modulation or multiplication, we create the upper sideband and the lower sideband, and there is nothing in between. When there is nothing in between, we call that nothingness the virtual carrier. It should be there, but it's not. But it's not there purposely. We don't want it there, again, because this is a game of how much power we have and what do we do to invest most of the available power all into the intelligence we want to transmit. So purposely we introduce the balanced modulator, and that's its output spectrum. While I'm stretching it now, we probably have to go very soon. One more and I quit. I just finished this page. This is again the spectrum of a double sideband signal compared with a single sideband signal. This is purposely done because you notice the double sideband signal, at number 10, that could be 10 megahertz, there is the virtual carrier. Virtual is not there. It could be, but it's not, so we call it virtual. So the 10 megahertz will be just a marker. It's not there. Above it, there is the upper sideband. and below it is the lower sideband. So if we manage to eliminate one or the other, either one, by some electronic means, suddenly the available power we have is not sent into both. Just the one component kept no benefits of the whole total available transmit power. So the transmit power apparently doubled, because it's not half of it is going in one sideband and the other half into the other sideband, but the whole available power is going into just one single sideband we transmit. When something doubles like this, probably in one of your early lectures weeks ago, you learned about the decibels. So when you double something, then you increased your transmission by the amount of 3 decibels. 3 decibels has the meaning of doubling it. Again, it's easy to explain this with a mathematical equation, but we don't go into logarithm and inverse log now. So that was that. And is this the end of this page?
Yeah.
It is.
Then the page 4.
Well, do we have another page or angle modulation? Remember the angle of a sinusoid? A sinusoid has the brackets. In the brackets is 2 pi ft. This is the angular velocity plus a little phase shift. When we perform angle modulation, we either modify the frequency or we modify the phase angle to perform frequency modulation or phase modulation. Well, phase modulation is used a great deal in cell phone technology. Well, your voice is eventually sent to a analog to digital converter, and digital bits are going to phase modulate a carrier or code modulate a carrier, and that is being sent from the cell tower toward your cell telephone. You have a sinusoid, which is a higher frequency, and a lower frequency intelligence. So the carrier is high frequency and the intelligence is low frequency. A little up, please, and we see the result of those two. Okay, this is easy to demonstrate in the laboratory. When I work at Sub College, all of my students could demonstrate this on available equipment in the laboratory, but you actually need a whole laboratory with specialized signal generators that they have modulators in them, and you can send in the intelligence, modulate and display this. It's a fun way to display it in the laboratory. Right now you just have to believe me that this is what it would look like on the oscilloscope. The human eye cannot distinguish the oscilloscope view of a phase modulated or a frequency modulated wave, because the differences are so small that the eye just cannot resolve. So no one can look at this wave and declare it for certain that this is phase modulation or this is frequency modulation. So to be on the safe side, you say, oh, it looks like angle modulation. Well, angle modulation is either frequency or phase modulation. There are differences, and what are the differences? The differences are in the frequency domain. When you transmit the signal, those various components that they are present in the frequency domain, they have a somewhat different distribution for phase modulation or for frequency modulation. Well, I would love to go on and on till 12 o'clock, but probably we should quit here. Thank you very much, and thank you, Bruce. This was borrowed time. Based on past year's experience, we learned that this is a big chunk of material, modulation, transmitters and receivers, and I was just zipping through it too fast.